A force acts on a ball through a bat. So for a short interval of time, we call that force as an impulse force. When I take out the m, which is common in both the terms, it is final minus the initial velocity divided by time t proportional to f. What is inertia? Newton's first law is also called law of inertia. It is the tendency of the object. Hello everyone, welcome back to each one of you for my new session on a new chapter, Laws of Motion. I am Nishmananjama, Faculty of Physics in Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. Today we shall discuss chapter 5, Laws of Motion. This is the first session where we will be studying Newton's laws of motion. What is this laws of motion? Who is Newton? Laws of motion was given by a scientist, Newton. Laws of motion has a very mathematical and physical significance. Laws of motion is useful to describe the motion of universe, and it has a lot of applications in every field. So, who is Newton? Newton is an astronomer, he is a mathematician, he is a physicist, and he is a philosopher. So, Newton came up with his 3 laws, first, second and third law. He introduced all the laws of motion in his book called Mathematical Principle of Natural Philosophy, which is also referred as Principia. So, I also came up with universal law of gravitation, which explains about gravitational force. So, his book, this one volume consists everything in it, every foundation of a classical mechanics. So, Newton's laws of motion. Today's session is about Newton's laws of motion. So, let us first try to understand Newton's first law of motion. What does it explains us? So, Newton's laws of motion. So, this is the Newton's first law of motion. First law of motion. Consider you have a straight line. Consider you have a straight line where I have a football. Where I have a football located at point A. I want to move this football from point A to point B. I want to move this football from point A to point B. I have a football on the straight line on the football ground. I want to move the football from point A to point B. Now what I'll do? I'll look at the football. But still the football is not moving. I'll strongly look at the football. But still the football is not moving from one point to another point. It is still at the rest state itself. I'll ask the football, please move from point A to point B. Will the football move? I'm telling the football, please move from point A to point B. But still it is not moving. What I'll do? I'll apply a force F. I'll apply force F on the football. It will start moving from point A to point B. It will start moving from point A to point B immediately when after I apply an external force on the ball. So what does this example tells you? What does it means? So a football is initially at rest. It wants to remain at rest. It wants to remain in the state of rest. So the tendency of the ball to remain in the same state, unless and until it is compelled to change that state, by applying an external force on it, This is in case of rest. What if you are moving in the straight road with a car? You're driving a car along a straight road. You're moving with a uniform velocity. You're moving with a constant velocity in the straight road. So that means you're in motion. You're moving with a car in the straight road. That means you're not in rest. You're in motion with constant velocity. When will you change this state of motion? Now I'll apply a sudden brake. What will happen? The car will stop immediately, which is moving in the straight road. It will stop immediately. In order to stop the motion of the car, what am I doing? I am applying the brake. That means I am applying a force. I am applying a brake. That means I am applying an external force to stop the motion of the car. To stop the motion of the car. If you don't apply any force, the car will be in continuous motion. So you don't want to change its state of uniform motion. So the tendency, the property of the car or object to remain in uniform motion unless and until you compel to change that state of uniform motion, unless and until you compel it to change that state by applying an external force on it. This is what is explained in Newton's first law. That is why I said Newton's law of motion has mathematical and physical interpretations. It is helpful to explain the motion in universe, and its application is really limitless. So now with this example, I hope now if you read Newton's first law, it will be clear for you. What does it state? It is very important. Newton's law of motion, the law of motion chapter 5, it is very, very important. So what it states? Every body, either it is ball or it is car, every body or object continues to remain in its state of rest, very important, in its state of rest or uniform motion, in its state of rest or uniform motion along a straight line, unless and until, till when it will remain in the same state? Unless and until it is compelled, it is forced to change its state by an external force that applied to it. So every body continues to remain in its state of rest or uniform motion along a straight line unless it is compelled by an external force to change that state. Unless it is compelled, applied with an external force to change that state. So, example for Newton's first law of motion. Passenger swinging a turning bus. Passenger swinging a turning bus, immediately when the bus takes right or left, you swing with that, taking a walk, etc. Newton's first law is also called law of inertia. What do you mean by this? Newton's first law is also called law of inertia. What do you mean by inertia now? Inertia is nothing but the tendency, the property of the object due to which it resists the change of state of rest or uniform motion when external force is applied on it. So what is inertia? Newton's first law is also called law of inertia. It is the tendency of the object. What is inertia? What is inertia? It is a tendency of an object due to which it resists the change of its state of rest, or uniform motion when external force F is applied on it. So what is inertia? It is the tendency of an object. Due to that property of the object, it will resist the change of its state of rest or uniform motion when external force is applied on it. take an example and explain this. I'll take an example of moving bus, of moving bus, a passenger in the moving bus. You can see here a passenger in the moving bus. So suppose if you are moving in a bus, when the bus is at rest and starts immediately, when it immediately comes to motion, you will feel a backward jerk. Similarly, when you are moving in the bus, that means the bus is in motion, and when the sudden brake is applied, you will feel a forward jerk. Isn't it? You will experience this in your day-to-day life. Have you ever wondered why is this happening, forward and backward jerk? What is the reason behind it? That is due to inertia. It is a property of the object of the body. So let us try to understand with this example, which I said, a passenger in a moving bus. So suppose you are in the bus is at rest, you are sitting inside the bus, so you are the passenger in the bus, you are at the rest position. When you are at rest, your leg is connected directly to the floor. Your lower body is connected directly to the floor. That is, the upper body is indirectly connected to the floor. It is not direct contact with the floor. So when the bus starts immediately, when from the rest position, when it immediately comes to motion, your legs, that is your lower body, is directly connected to ground, that is floor. It will accept the change soon. So it will start to come into motion. Whereas your upper body is not directly connected to the floor. So what you will feel? You will feel a backward jerk. That is due to your upper body is not ready to accept that change immediately, because it is not directly in contact with the floor. It takes a moment to change its state and come into motion. That is why you feel a backward jerk. You can see here, if you are not holding with the proper support and if you are not ready to change your state when the bus comes into motion, you may fall back. You can see a forward jerk. Since your lower part of the body is directly connected to the ground, when bus is at rest, when it comes to motion, your lower body will accept the change soon. It will come to motion soon. Whereas your upper body, which is not in direct contact with the ground, will take a moment, will take a few time to come into motion. That is why you feel that backward jerk. That is due to inertia. The tendency of the body, that property of the body due to which it is opposing the change of its state of rest, when external forces applied on it. Similarly, what happens when you are in motion? When you are in rest and come into motion, your lower body will accept the change. It will immediately come back to motion, come into motion. But your upper body takes a moment and then it has to change its state. That's why from the rest it come into motion. When you are in the moving bus, you are traveling in a bus. You are moving in a bus with a constant velocity. Now what is in this case? What happens? You are moving. So when you are moving in the bus with constant velocity. You can see here your legs. So bus starts. When bus starts, your legs, lower part of the body will accept the change soon, whereas your upper body will take time to come into motion. That's why you feel that backward jerk. You can see. And when the bus is in motion, you are sitting in a moving bus. Your legs are in motion. So your legs are in motion. When sudden brakes are applied, immediately your lower body, your legs will just in direct contact with the ground, will come into rest. Whereas your upper body, which is not directly connected to ground, will be in motion itself. That's why you feel that forward jerk. You can see. That's why you're sitting. You are moving in the bus. Your legs are connected to the ground. When The bus stops suddenly, the legs immediately come into rest, whereas your body takes a moment to come into rest. It will be still in the state of uniform motion. That is why you feel that forward jerk. That is because of inertia. Did you observe this tendency of the body? This tendency, the property of the body. So that is why this property of the body is due to which it resists the change of its state of rest or uniform motion when external forces applied on it. It takes time to accept the change when external forces applied on it. So we took the example of the moving bus, a forward jerk and a backward jerk. Then I have this question. So whether all the objects have same inertia? Take the example of table. And second, chair. You know what is table and chair? In order to push the table that has large mass, table has more mass compared to chair, right? So what happens? I need to apply large force. In case of chair, which is lighter than table, which has less mass than table, so it has less mass. So should I apply more force to push the chair? A little force is enough in order to push the chair compared to table. So you need just less force. So more the heavier the mass, more is inertia. Lesser the mass, less is inertia. So every object does not have same inertia. If the heavier the mass, heavier is the inertia. Lesser the mass, lesser is the inertia. If it is heavier, then the object will have more inertia. That means it will resist to change its state of rest or uniform motion. That's why you have to apply large force. When you have less mass, for example, chair, when there is less mass, the inertia will be less. That is, the inertia is property of the body to resist the change of state or motion, change of state or uniform motion. So less force is enough to push the chair. So this is about inertia. And based on frame of reference, we have two types: inertial frame of reference and non-inertial frame of reference. We have studied in the previous session to describe the motion of the object. We need a frame of reference. The previous session, we have clearly studied based on frame of reference how we observe the object at distance, how we observe the objects which is at different location based on our frame of reference. So we have two types: inertial frame of reference and non-inertial frame of reference. Inertial frame of reference is where the Newton's first law is valid. If Newton's first law is valid, it is called inertial frame of reference, where all frame of reference is moving with constant velocity with respect to inertial frame. It is moving with constant velocity with respect to inertial frame. So they are called inertial frame of reference. What is non-inertial frame of reference then? So the frame of reference where Newton's first law is not valid is called non-inertial frame of reference. That means all frames are not moving with constant velocity. All frames are moving with some acceleration with respect to the inertial frame. They are called non-inertial frame of reference. So what is Newton's first law? I hope it is clear. Every object tends to remain in the state of rest or in the uniform motion unless and until it is compelled to change its state of rest or uniform motion by applying an external force on it. This Newton's first law is also called law of inertia, and we studied what are the laws of inertia. Tendency of the body due to which it resists the change of state or uniform motion when an external force is applied on it. So it will resist the change of state. If it wants to be at rest, it prefers to be at rest. If it wants to be in motion, it prefers to be in motion itself. So that opposingness is there. If it wants to be in rest, it wants to be in rest. If it wants to be in motion, it wants to be in motion itself. But unless and until when we apply an external force, we are compelling it to change its state of rest from, if it is rest, first change the state of rest to uniform motion. If it is moving with uniform motion, we compel it to change its state by applying an external force from motion to come into rest. So this is about Newton's first law. Next, we have Newton's second law. So understanding Newton's second law is important because using this Newton's second law, we explain Newton's first law and Newton's third law. So Newton's second law of motion gives a relation between acceleration. It gives a relation between mass and force. So Newton's second law gives a relation between acceleration, mass and force. So what does Newton's second law state? What does Newton's second law state? It states that the rate of change of momentum, of body is directly proportional to the force acting on it and takes place in the direction of force, and change in momentum takes place in the direction in which force is acting. So rate of change of momentum is directly proportional to force applied on it and takes place in the direction of the force. So what is this? F is proportional to delta P by delta T. We know force and momentum are vector quantity which gives us both magnitude and direction. So what is momentum? Momentum is nothing but given by symbol P. It is in simple the quantity that has mass into that quantity that gives mass into velocity, mv. Momentum is mass into velocity. So Newton's second law of motion, what are the example? Consider this example of pushing a car and pushing a small load of weight here with a trolley bag. So you can see here, pushing this and pushing this, which has larger mass. Obviously car has large mass, so you need to apply more force in order to push it because the inertia will be more. So when you apply large force, what happens? Acceleration will be more. Acceleration produced will be more. So in this case, F is proportional to A. Consider this case. Instead of car, you are pushing a trolley bag. Compared to this has a less weight, which has less mass. So when it has less mass, inertia, the tendency of the object to resist the change, inertia will be less. When inertia is less, only little force, you can see the difference how they are pushing it. A little force is enough to move the luggage of this trolley bag. So when you just need little force to push this small mass, that means F is proportional to M. So from 1 and 2, I can say F is proportional to M and F is proportional to A. F is proportional to MA. From this format, we came into F is equal to F proportional to MA. From this form to this form, how did I frame the first form? How did I reduce from first form? How did I come from first form to this form? How did I arrive at from this form of the statement to this form? That we will derive a derivation for expression of force where we'll show F is proportional to MA. Similarly, you can see one more example here. You have a person is pulling a weight which has a person is pulling a mass which has 10 kg and a person is pulling a mass which has 20 kg. So which has more mass here? This or this? The second person has more mass with him. That means inertia will be more. So he is applying more force to pull it. So acceleration comes into picture. More acceleration will be produced. So F is proportional to A. This is 10 kg mass. The little force is enough to pull this weight because mass is less, inertia is less. That is why if mass is less, inertia will be less. So little force is enough. So F is proportional to M. So I can write F is proportional to MA. F is proportional to MA. So from this format of the statement, I came to F is proportional to MA. How did I arrive from this form till this form? We'll derive an expression. I hope the statement is clear for you. The rate of change of momentum of the body is directly proportional to force acting on it and takes place in the direction of force. Imagine pushing a car or a truck. What is the mass of the car and what is the mass of the truck? So truck will have large mass. So you need more force to push. Acceleration will be produced more. So F is proportional to A. Car, a little force is enough compared to truck. So you'll apply only little force because mass is less, inertia will be less. So F is proportional to M. So we got from the two case, F is proportional to ME. How did we arrive at that? We look at this derivation for Newton's second law. So expression for force. We'll derive an expression for force. What does the statement of Newton's second law says? The rate of change of momentum. If it is just change of momentum, when I talk rate of change of momentum, I have to divide the term with respect to time. When I say just change of momentum, it is nothing but P is the final momentum. Total momentum P is equal to final momentum minus the initial momentum. Momentum is a vector quantity. Final momentum minus the initial momentum. So what is momentum formula? P is equal to mv, mass into velocity. If I substitute, I'll get total momentum. What is mv? If I take the final velocity as mv, I will take the initial velocity, initial momentum as m into initial velocity denoted by u. So total momentum is final minus the initial, mv minus the initial momentum where the velocity is mu. So taking m common, you will get v minus u. So this will give you the change in momentum, not rate of change of momentum. You will get m of v minus u. Instead of u, we can take it as v1 as initial velocity and v2 as final velocity. If that is the case, you will get the final velocity minus the initial velocity. So it is all the representations how you denote it. I will take it as v as the final velocity, u as the initial velocity. But your statement says it's the rate of change of momentum of the body. So rate of change of momentum. So I will write it as delta. This describes the change. Delta P by delta T, because it is the rate of change of momentum of the body. So I have to divide the momentum with respect to time, and delta indicates the change. So that is proportional to force. So what I will do, when it is change, consider I have a object A, which is initially at time 0 with initial velocity u. From initial velocity, as time increases, it will move towards the object, it will move towards position B. So initially it was at 1, it was at A. With time increases, at time tends to t, from 0 to time t tends to t, the object will move from one position to another position, that is from position A to position B. So initially the velocity was u, the final velocity is v, where the mass of the object remains the same. How did the object move from A to B? I applied a force on the object to move from A to B. Consider a body of mass m, is moved, is applied with some force F. It has initial velocity u. It will move from point 1 to point 2. So the final velocity is given by v, symbol v. Now how will you derive this expression? So what is the change in momentum? What is the formula for momentum? It is mass into velocity. I want to know what is change in momentum. How do we calculate change? Final minus the initial. So what is the change now? It is mv minus mu. Final velocity minus initial velocity divided by time t. So you got the momentum. It is final minus the initial divided by time is proportional to f. So when I take out the m, which is common in both the terms, it is final minus the initial velocity divided by time t proportional to f. So what is v minus u by t? It is nothing but acceleration a. It is nothing but acceleration a. Change in velocity. What is change in velocity? Final velocity minus initial velocity by time. Change in velocity by time is nothing but acceleration. On substituting, you will get ma is proportional to f. It's proportional to f. It's a vector quantity. To remove the proportionality symbol, what I will do is ma, I will add a proportionality constant, say k here. So that is equal to f. The k from experiments is nothing but equal to 1. So f is equal to ma. This is how I arrive at the expression from this form to f is equal to ma. This is how you find out the change in momentum. But for the first PUC level, you have to follow the differentiation form of the Newton's second law of motion. You have to take the differential form of you have to find out what is the force. F is equal to ma, force in the differential form. For that, what I'll do, the same derivation instead of delta p by delta t, I'll have change in momentum by change in time is proportional to f. So what is p here? The p is nothing but momentum mv divided by dt proportional to f. So differentiation, you have learned differentiation. How will you differentiate the term now? Mass is constant. I'll take out the mass out. I'll differentiate v with respect to t. So it is dv by dt proportional to f. What is dv by dt? It's nothing but change in velocity by time. So it will be acceleration ma. I'll multiply a proportionality constant k to remove the proportional sign here, that is equal to f. K, we know proportionality constant value is 1. So I'll get ma is equal to f. This is the differential form of getting the expression for force. This is a differential form. For class 11, you have to adopt the differential form to derive the expression for force. You have studied this form of deriving the force in your class 9. So your textbook has a differential form of deriving the expression for force. By knowing F is equal to ma, you can calculate what is the force of the force applied on the object. Using this equation, you can get the value of force. Look at here, F is equal to ma. F is equal to ma. So what is m? M is measured in terms of kg, right? Acceleration is measured in terms of meter per second square. So you can see here kg meter per second square, that is nothing but equal to 1 Newton. So force is measured in terms of Newton and mass is measured in terms of kg. Acceleration is measured in terms of meter per second square. So you can write kg meter per second square as 1 Newton. Force is written as 1 Newton. 1 Newton is the unit to measure the force applied on the object. This is the derivation, how you derive the expression for force using Newton's second law of motion. Similarly, consider I have an example. For example, we have seen F is proportional to M and how F is proportional to A, and in an order F is proportional to MA. Similarly, for example, I have a ball. I have a ball which is initially at position A with initial velocity U. With initial velocity U. It is moved to object. The ball is moved to point B by applying a force F. The mass of the ball is 2 kg. So I am applying force. So force applied. So here you can see this example where I have a object which has initial velocity u and mass of that object, that is the ball, for example if it's a ball, it is 2 kg. So I'll apply some force to push the ball from position A to position B. So from the initial velocity, the ball will move with some velocity 5 meter per second. 5 meter per second. Similarly, in the second case, I have a ball which is initially at point A. I'll apply some force. Which has initial velocity u. I'll move the ball, same ball which has 2 kg of mass, to position B, to point B. The velocity will turn to be 10 meter per second. 10 meter per second. You can see here, I am applying the force to push the ball of mass 2 kg. The force, and here also I am applying the force to push the object which has same mass from one point to another point. See the velocity after it reaches the position B. Here 5 meter per second, here 10 meter per second. That means I have applied more force to push the ball which has same mass. I applied more force. More force is applied to push, that's why it has reached the velocity 10. Here I have applied less force, so it has moved only velocity 5 meter per second. I want to find out what is change in momentum. Not rate of change. I just want to know what is change of momentum. How will you find change of momentum? Final momentum minus initial momentum. When I say final momentum minus initial momentum, see, you have this formula, m of v minus u. On simplification, see, m of v minus u. M I know it is 2 kg. In case 1, this is case 2. M is 2 kg. And what is the final velocity? It is 5 minus initial velocity is 0. So it will be 2 5s are 10. The answer will be 10. What will be the change of momentum? It will be 10 kg meter per second. Kg meter per second. What happens in case 2? What happens in case 2? Mass is same. Mass is same, 2. But what is the final velocity? It is 10 because I applied more force. 10 minus initial velocity is 0. It is starting from 0. So, what is the value here? It is 20 kg meter per second. See this, 20 and 10. So, I need change of momentum. Here, change of momentum is 10. Here, change of momentum is 20. Here, change of momentum, it is less because I applied less force. Here in second case, change of momentum is 20 kg meter per second. That means change of momentum is more compared to case 1. Why? Because I am applying more force. So I can tell F is proportional to change of momentum. F is proportional to change of momentum. So more the force, more will be change of momentum of the ball. Less the force, less will be change of momentum of the ball. This is one example where you can see F is proportional to change of momentum. So this is all about Newton's second law of motion, which is very important, where you have to which gives the relation between A, M and F. Using this, we can calculate force acting on a object, which is very important for numericals. F is equal to ma. Keep in your mind. So next, you have impulse. You have impulse J given by alphabet J. You have impulse J. What is this impulse J? What does this impulse of force means? For example, it is the force acting on an object for a very short period of time. That force, we call it as impulse of force. We call it as impulse of force. A force, a large force, a force acting on a body for a short interval of time are called impulse of force. Impulse is given by alphabet J. Alphabet J. For example, a cricketer striking a 6. A cricketer hitting a 6. So, he is applying a large force for a very short interval of time. The ball is moving, covering a large distance. For example, you will shoot a glass. You will fire a bullet to the glass. Very short interval of time, we are applying large force. So, the glass will break into pieces. Very short interval of time, the force acting on it is called impulse of force. Here you can see an example. When batsmen play a shot for 6, a force acts on a ball through a bat. So, for a short interval of time, we call that force as a impulse force. You can see a video where a ball is hit by a bat and we use a gun to shot a glass piece. So, when a bullet strikes a glass, impulsive force acts on the glass. Very short interval of time, large force acting on an object. So, this is what we call as impulse. So, impulsive force is given by F is equal to, impulse force is given by F into T. Impulse of force is given by F into T. So, where impulse force is equal to F into T. You consider you have a body of a certain mass and you are applying a force in a very short interval of time T. So, that is called impulse force. If U is the initial velocity, V is the final velocity and A is the acceleration of the body. From the second law, we have F is equal to ma. F is equal to ma. What is F is equal to ma? It is, A is what? Change in velocity by time. We know that F of V minus U by T. This is F. Impulse is equal to, we have impulse is equal to Ft. So, we know what is F. It is m of final minus initial velocity by T into T. So, T and T get cancels. So, what is the impulse? That is equal to m of V minus U. M of V minus U. Impulse is equal to m of V minus U. What is m of V minus U? It is nothing but change in momentum. So, impulse of a force is equal to change in momentum, mv minus mu. M of V minus U is equal to mv minus mu. From second law, we know force acting on a body is equal to m into A. A is what? Change in velocity. Final velocity minus initial velocity by time. So, impulse is given by F force into time interval. Then Ft, we have know what is F here, m of V minus U by T. So, when T and T get cancels, the remaining will be mv minus mu. What is mv minus mu? It is change in momentum. Impulse is equal to, force of impulse is equal to change of momentum of the body. So, this is about impulse of force. For a short interval of time, a force acting on a body is called impulse of force. So, next we have Newton's third law of motion, which is very simple and it is very significant role. It has very significant role. Newton's third law of motion. To describe Newton's third law of motion, we always need two objects with respect to which we describe Newton's third law of motion. What does it state? To every action, there is an equal and opposite reaction. For every action, there is an equal and opposite reaction. Take the example of a ball. Take the example of the ball. You can see the ball. It hits the ground. So this is the action. In return, the ground applies the force back on the ball. It will pitch back. So this is the reaction. This is the reaction. For every action, we have an equal and opposite reaction. Equal and opposite reaction. When we bounce the ball on the floor, that is the action. In return, the ball comes up. The equal force is applied by the ground. So that is the reaction. So for every action, there is an equal and opposite reaction. Example, take the example of a swimmer. A swimmer pushes the water. He will push the water. So that is the action. He will push the water. That is the action. And water will push him forward in return. So that is the reaction. Water pushes him forward. You push the water. That is your action. In return, the water pushes you forward. So that is your reaction. For every action, there is equal and opposite reaction. So these are the two examples, bouncing ball and a swimmer, which explains Newton's third law of motion. For example, you have two objects. So this is the object A and object B. Object A applies the force on object B. So that is FAB. So in return, object B applies the force on object A. It will be force applied by object A due to B. But it will be in opposite direction. FAB is equal to minus of FBA. So when you apply a force on the object, that is a reaction. In return, object B applies the force on A, that is a reaction, but it will be in the opposite direction. FAB is equal to minus FBA. Force applied on A with respect to B is equal to force applied on B with respect to A. So this is the Newton's third law of motion. For every action, there is equal and opposite reaction. So this is the third law of motion given by Newton, physicist Newton. So these are the three laws of motion given by Newton. So in this chapter, laws of motion is very important. Understanding the laws clearly with example is essential. So in today's session, we studied Newton's first law, Newton's second law and Newton's third law of motion. What first law states? If a body is at rest, it tends to be in rest unless it is acted upon by a force. If a body is in uniform motion, it tends to be in uniform motion unless and until it is acted upon by an external force. So what does Newton's second law states? The change of momentum, the rate of change of momentum is directly proportional to force applied and acts in the direction of force itself. So then we derived the expression for differential form of force, and we saw the example where F is proportional to change in momentum. That is, more the change in momentum, that means more force is applied. Less force is applied, less change in momentum. We also saw F is proportional to ma. And we studied what is impulse of force. Force applied on a body on a very short interval of time. A cricketer hitting a six or a bullet striking a glass are the example for impulse of a force. Third law, every action there is equal and opposite reaction. That is, for example, bouncing of a ball. When you bounce the ball, that is the action. In return, the ground applies the force to pushes it back. That is your reaction. So for every action, there is equal and opposite reaction. You always need two objects to describe this law. A ball as well as the ground. A swimmer, a person who is swimming as well as the water. With these two objects, we describe Newton's third law of motion. That's all for today's session. Next, I'll come up with more interesting sessions on laws of motion where we'll solve the interesting numericals and also we'll study the linear momentum and other interesting topics under this chapter. Until then, take care. Have a good day. Thank you.